Permutations and combinations, lesson 7, Pascal's triangle. So we're kind of changing work a little bit here. We're kind of going to the second part of this unit. So second part is all about doing some expansion. So we're going to start by looking at the expansion of x plus y to the power of n. So in this section we will investigate patterns in the expanded form of x plus y to the n for n less than or equal to 4. So here we're basically foiling things out. So the first ones are easy. X plus y to the 0 is 1. We know anything to the power of 0 is 1. And x plus y to the 1 is simply x plus y. Well, now what about x plus y squared? Well, remember this is x plus y times x plus y. So when we FOIL out and combine like terms, we have x squared plus 2xy plus y squared. Next we want to look at x plus y cubed. Well, this is really x plus y times x plus y times x plus y. Or we can think of it as going x squared plus 2xy plus y squared. That was it squared, and then we need to multiply this by x plus y. If we expand that and collect like terms, we get x cubed plus 3xy plus 3xy, sorry, this should be plus 3x squared y plus 3xy squared plus y cubed. And lastly, if we have x plus y to the 4, this is x plus y multiplied by itself 4 times. And again, you could then take this previous polynomial and multiply it by x plus y. And when you expand it out and combine like terms, you're going to have x to the 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4. So complete the following using the answers above. So we have x is 1, x to the plus y to the power of 0 is 1, x plus y to the 1 is x plus y squared is x squared plus 2xy plus y squared. X plus y cubed is x cubed plus 3x squared y plus 3xy squared plus y cubed. And x plus y to the 4 is x to the 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus, y to the 4. Y to the 4. So state the number of terms in each in the expansion. Well, x plus y squared had 3 terms. X plus y cubed had 4 terms. X plus y to the 4 would have 5 terms. So following the pattern, we notice we have one more term than the degree. So if we have the power of 20, that means we have 21 terms. State the sum of the exponents in each term in the expansion. So if we look here, x plus y squared, we have x to the 1, y to the 1. Adding those two exponents gives us, gives us the number 2. Gives us the exponent 2. If we look at x plus y cubed, if we add the exponents, well, here we have a 3. Here we have x squared, y to the 1. 2 plus 1 is 3. Here we have x to the 1, y squared. That also equals 3. Here, x plus y to the 4, well, we have x to the 4, that adds to 4. X cubed, y to the 1, if we'd add those exponents, it equals 4. We notice they'd all equal 4. So in this case, we see that the sum of the exponents is equal to what the exponent was. So x plus y to the 20 would have 20. So complete the following arrays which show the coefficients of the terms in each of the expansions. So now I'm just interested in the coefficients. So here I had 1, here I had x plus y, so my coefficients were 1 and 1. Keeping going, I had 1, 2, 1, then 1, 3, 3, 1, then 1, 4, 6, 4, 1. If I wanted to make that into a triangle, I just kind of center all the coefficients. Explore the patterns in the triangle array and complete the next row. So if you look at this, first of all, we see that everything on the outside has a 1. So my next row is going to have 6 numbers. And I see that everything on the outside is 1, so I can fill in the 1. So now let's see if we can find the pattern. Well, see here, if I add 1 and 1, I get 2. If I add 1 and 2, I get 3. 2 and 1 make 3. Here, 1 and 3 make 4. 3 and 3 make 6. 3 and 1 make 4. So here we're going to have 1 plus 4 is 5. Here, 4 and 6 is 10. 6 and 4 is 10. 4 and 1 is 5. So that would complete the last row. Properties of the expansion. So this is just showing it again in a triangle, and it's now completed that expansion that we found the pattern for. So now, since we followed the pattern, we can say that this would be the expansion of x plus y to the power of 5, because we could find the coefficients using that pattern. So there are always n plus 1 terms. So if our power is 5, we have 6 terms. If our power is 4, we have 5 terms. The sum of the exponents of x and y in each term is equal to n. So we notice here, when we add the exponents, it equals 5, because that's what our power was. The exponents of x decrease term by term. So we start with x to the 5, and we end up with x to the 1, and then x to the 0. Well, the exponents of y increase term by term from 0 to n. The coefficients in each expansion form a symmetrical arrangement. So this is essentially what we call Pascal's triangle. So the coefficients in the above expansion can be put into a triangular array known as Pascal's triangle, named after a man called Blaise Pascal, who developed applications of the triangle in the 17th century. Use the pattern to complete the next 3 rows of Pascal's triangle. So remember, we said the outside was 1, then we start adding these things up. So 1 and 5 is 6, 5 and 10 is 15, 10 and 10 make 20, then it's symmetrical, so it keeps going. So we want the next 3 rows. So that was 1, that's 2, and we can keep going. 1, 8, 28, 56, 70, 56, 21 and 7 is 28, 7 and 1 is 8, and then our outside is a 1. So complete the following expressions. Well, x plus y to the 6th. So we know this row represented x plus y to the 5, so x plus y to the 6 is going to start with 1x to the 6. My next term is going to be 6. Again, the smartboard is cooperating perfectly. So I'm going to have 6. That comes from this row here. And x decreases and y increases. So my first term is going to be x to the 5 times y, plus my next number is 15. X is going to decrease, y increases, noting our exponents still add up to 6. Next number is 20. X goes down, y goes up. Next number is again 15. X goes down, y goes up. Now we're back to 6. And lastly, we have 1, y to the 6. Same idea with the exponent x plus y to the 7. I'm now working with the next row. So I have x to the 7 plus 7x to the 6y plus 21 x to the 5y squared plus 35 x to the 4y cubed plus 35, x to the 3, y to the 4, plus 21, x squared, y to the 5, plus 7x, y6, plus y to the 7. So the numbers from that row are my coefficients. My exponents always add up to 7, and I'm decreasing x, increasing y. Which row of Pascal's triangle is equivalent to the coefficients of the terms in the expansion of? Well, x plus y to the 6. So that was this row here. So that is 1, 2, 3, 4, 5, 6, the 7th row. Which makes sense because our first one was representing x to the 0. So our second row represents x to the 1. So this would be the 7th row. X plus y to the 7th would be the 8th row. The 12th would be the 13th row. The nth would be the n plus 1th row. Now we can actually write Pascal's triangle using our combinations. So 1 can be represented as 0, choose 0. 2 can be represented as 1, choose 1. Sorry, row 2 can be represented as 1, choose 1. Sorry, can be represented as 1, choose 0, and 1, choose 1. The third row can be represented as 2, choose 0, 2, choose 1, 2, choose 2, and so on. State the first 3 terms of the 8th row of the Pascal's triangle in numerical form and in combination form. So the 8th row, so the next row that we did look at on the previous page, but we can do it here again. It'll be 1. Then we're going to go 1 plus 6 is 7. 6 plus 15 is 21. So those would be our first 3. We're in the 8th row. Notice the first row was 0, choose 0. So the 8th row will be 7, choose 0, 7, choose 1, 7, choose 2, all the way up to 7, choose 7 if we wanted to finish off the row. So state the last 3 terms. Well, the last 3 terms are the same thing, but in opposite order because we know it is symmetrical. So what's going to be equal to 7, choose 2? Well, that would be 7, choose 5, 7, choose 6, 7, choose 7. Use Pascal's triangle to write the following as a single combination. 4, choose 2, plus 4, choose 3. So 4, choose 2 is here. 4, choose 3 is here. We know then they must add to give us 5, choose 3. 6, choose 0, 6, choose 1. 6, choose 0, 6, choose 1. Well, that's representing these numbers here. Well, when I add them together, here I got 7, and I know 7 was 7, choose 1, so this would be 7, choose 1. N choose R plus N choose R plus 1. Well, this becomes N plus 1. Oops. N plus 1 choose R plus 1. Investigating 3 sums equal to 2 to the n. Complete the table for the sums of the numbers in each of the first 6 rows of Pascal's triangle. Complete the following statement. The sum of the numbers in the n plus 1th row of each Pascal's triangle is. So let's look at this. Sum of the numbers in the row. So we're just adding up the coefficients. First one is 1. First one is 1. Second one is 2. Then 4. Then 8. Then 16. Then 32. So looking as powers of 2, that is 2 to the 0, 2 to the 1, 2 squared, 2 cubed, 2 to the 4, 2 to the 5. So following this pattern then, in the nth row it would be 2 to the n minus 1. In the nth plus 1 row it would be 2 to the n. So the sum of the triangles, the sum of the number in the rows is 2 to the n. Look at row 5 in Pascal's triangle in a combination form. The sum of the numbers in this row can be written as 4 choose 0 plus 4 choose 1 plus 4 choose 2 plus 4 choose 3 plus 4 choose 4. Refer to part 1 and express this as a power of 4. Well, this would be 2 to the 4. We know that this is representing the fifth row, and it has 4, choose 0. Remember, the first row started with 0, choose 0. Look at row 7. So this sum would be 2 to the 6. Complete the following statement. We now have n choose 0 plus n choose 1 plus n choose 2 all the way up to n choose n. Well, this would now be 2 to the n. Well, we know those triangles were really just representing the sum of the coefficients, so this is going to give us the exact same chart. The sum of the coefficients were 2, 4, 8, 16, and 32. Written as powers of 2 would be 2 to the 1, 2 squared, 2 cubed, 2 to the 4, 2 to the 5. And then n would be 2 to the n. So the sum of the coefficients in the expansion is 2 to the n. The following statements summarize the previous investigative work. So this is the important part. The sum of the numbers in the nth plus 1th row of Pascal's triangle is 2 to the n. N choose 0 plus n choose 1 all the way up to n choose n is also 2 to the n. The sum of the coefficients in the expansion x plus y to the n is 2 to the n. So these all represent the same thing, so it makes sense they're all equal. Determine the sum of the numbers in the 10th row of Pascal's triangle. So remember, it says the sum of the numbers in the nth plus 1 row is 2 to the n. So that means we're talking about the 10th row. That means we're looking at the 9th plus 1th row. So the sum is going to be 2 to the 9, which is 512. Secondly, determine the sum of the coefficients in the expansion m plus n to the 12th. Well, we know this is equal to 2 to our exponent, so this is 2 to the 12th, which is 4096. C, determine the value of 15 choose 0 plus 15 choose 1 all the way up to 15 choose 2. Well, we discovered that this is 2 to the n, so that's 2 to the 15, which is 32,768. This one here, 6 choose 0 plus 6 choose 1 plus 6 choose 2 all the way up to 6 choose 5. Well, we know that this would be 2 to the 6, except we didn't include that last term. 6 choose 6. 6 choose 6 is just equal to 1, so this is 2 to the 6 minus 1, which equals 63. Okay, there's one more section to this lesson. Recall the following problems from lesson 3. Paul and Catherine are considering the following problem. Find the number of routes from A to B if paths must always be move closer to B. Catherine's method was to use permutations with repetitions to get 5 factorial over 3 factorial times 2 factorial, which is 10 roots. This answer can also be determined with Pascal's triangle. A, there is one root from A to C. This number has been placed on the second diagram. Determine the number of roots from A to the points D, E, F, G, and H. Write the answers in corresponding positions on the second diagram. So we have rotated it, so that's so because we're going to use this to be Pascal's triangle, so it's going to kind of look on a triangle. So from here, there's one way to get here and one way to get here. Following down the sides, we have one way, one way, one way. Right? We can only go straight down the sides. To get to this point here, I can either come this way or this way, so that gives me 2 paths. So just like the Pascal's triangle, I can get this from adding. To get to this point, I can either come from here or from here. Well, I had 2 ways of getting to here, so this gives me 2 unique paths. Plus, I could come this way, so that gives me 3. Similar reasoning gives me 3 here. And now I start to see the pattern that I really just add up from the vertices that I came from. So to get to this vertex here, I can come this way or this way. So I have 3 paths to get here, 3 paths to get here. That gives me a choice of 6 paths to get here. Same way here, to get to this point, I can come from this direction or this direction. That gives me 4 total paths, 10 paths to get to the last one. So how do the following answers relate? F compared to C and D. Well, F was really equal to C plus D. H compared to E and F, well, H was equal to E plus F. I compared to F and G, I was equal to F plus G. Use the relationship in B to complete the second diagram and compare your answer with Catherine's. Well, the answer is the same. And equals 10. So we can do it using, whoops, not 0, equals 10. So we can do it using permutations, or we can do it using this Pascal's triangle method. So the exploration on the previous page can be used to illustrate how Pascal's triangle may be used to determine the number of roots in a diagram. Notice the numbers on the diagram on the previous page are part of Pascal's triangle as shown in the overlays below. Now we just laid it over top. So shown in the second diagram, the answer 10 is equivalent to 5 choose 3, which does equal 10. So I'd say it's more handy to remember the pattern from Pascal's triangle rather than the actual triangle when we're answering these questions. So supervisor of the city bus department is determining how many routes there are from the bus station to the concert hall. Determine the number of routes possible if the bus must always move closer to the concert hall. So the first thing we can do whenever we're doing these is we're starting at this point, we can fill in ones at each vertex. We're only filling in at the vertex or the points. And we can always do the ones around. Now we start to add. So to get to this point, I can come here or here. 1 plus 1 is 2 routes. To get to this point, I can come from here to here. 1 plus 2 is 3 routes. To get to this one, I can come from here to here, which gives me 4 routes. Same thing on the next row. I'm going to go 1 plus 2. That's going to give me 3 here. 3 plus 3 gives me 6 here. 6 and 4 gives me 10. 1 plus 3 is 4. 6 plus 4 is 10. 10 plus 10 is 20. 1 plus 4 is 5. 5 plus 10 is 15. 15 plus 20 is 35. Now this 35, I can only move to the right from this one path, so I can copy that number down the edge. And now I start to add. 35 and 35, I have 70 ways of getting here. 70 plus 35 gives me this, which is 105. 70 and 35 gives me this, which is 105. So in total, I have 210 ways to get to the concert hall. If we wanted to use permutations with repetitions, well, I'd first deal with the first rectangle there. So I notice I have to take 7 steps in total because I have 3 going this way. 1, 2, 3, and 4 going this way. So that's 7 steps in total. Divide by the repeat in direction. Same idea for the bottom one. I see that I'm going to have to make 4 steps in total. 2 going each direction. And this is going to give me the same answer. It's really up to you what you find easier to do here. These ones get a little bit trickier. So a taxi company is trying to find the quickest route during rush hour traffic from the train station to the football stadium. Use Pascal's triangle to determine the number of different routes that must be considered if each intersection the taxi must always move closer to the football station. So using our pattern here, I always start by filling in down each side once. And now I'm going to start adding. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. The only way to get here is to come straight this way. So this one also needs to be a 4. 1 plus 2 is 3, 3 and 3 is 6, 6 and 4 is 10, 10 and 4 is 14. Next row, 1 and 3 is 4, 4 and 6 is 10, 10 and 10 is 20, 20 and 14 is 34, 1 and 4 is 5, 10 and 5 is 15, 20 and 15 is 35, 35 and 34 is 69. Only way to get to this point is to come straight down, so this is 15. 15 and 35 make 50. 50 and 69 make 119. So I have 119 ways. Explain why the permutations with repetitions formula 9, factorial over 4 factorial times 5 factorial does not work. Well, because we have this little gap here, we can't just separate it into two triangles. So this one is the hardest example of these what we call pathway problems, and you'll need to use the idea of Pascal's triangle for this one.